Hello guys, welcome back to the channel. It's Hashim. Today I'm going to show you how to draw shear and moment diagram for this problem. As you can probably see, this is the problem. It's 7.7-51. So let's get started. I'm going to convert this triangular distributed load into point load. In order to do that, you have to multiply by its area. 1.5 times 3 divided by 2, which will yield approximately 2.25 kilonewton. And I know that this distance from the centroid till the head will be 1 meter, because L by 3, and this distance to be 2 meters. 2 over 3 times L, which is 2 meters. I'm going to find the reactions. I'm going to take a moment at B, and I'm going to assume AY to be upper direction, so I'm going to assume clockwise to be positive. I have AY times 3, the lever arm between distance B, and I have 2.25. It will cause counterclockwise moment about point P, right? So minus 2.25 times 1 will equal to 0. Now AY, if we calculated it, AY will be equal 0.75 kilonewton. And in order to find BY, I have to take the summation in the force direction to be positive, to be 0, I have AY, which is 0.75 in the upper direction, as I calculated before, minus 2.25, and plus BY will equal to 0. Now BY will be equal, just add this together, will be equal 1.5 kilonewton, and I'm going to draw them here in order to start the shear and moment diagram process. I'm going to delete this portion, and let's get started. I'm gonna prepare for the shear diagram. I'm gonna start by shear diagram. As you can see, I draw a table, and let's get started. I have in the joint A, I have 0.75. I'm gonna go up 0.75 because positive. I'm going to go here. This is 0.75. The shear here is 0.75, and I'm gonna go minus 2.25. This total load. I'm gonna end up to here, minus 1.5 and plus 1.5, and I go back to 0. Now the problem here, how can we draw the shear diagram for this triangular shape? How the beam will behave under this load? Actually, you have two methods. You have the first method is to draw and from slow to fast, or you have to take moment function and shear function and calculate the area. According to the function, you will know how the shear will react. So I'm going to use slow and fast. The beam goes slowly. The load goes slowly till fast. So slowly, slow, fast. It will be like this. Slow, fast. As you can see, I'm going to call this distance to be x, and this point, which is the zero shear force. The shear force here is 0. We know that when the shear force is 0, that the moment will be maximum. The moment will be maximum. This is the maximum moment and 0 shear force. And in order to find x and calculate this area, shear area, and find the moment max, I have to do some manipulation, and I'm going to draw a line here, and I'm going to take similar triangles. If I call this point W, the maximum shear point W, and this distance to be x, as you can see, I draw it here. Now I can take the whole triangle and find W. Okay, this is the whole triangle. You can see, and find W. This is 1.5 kilonewton, I think it was 1.5. As you can see, it is here 1.5 here, and I have W here. I have here W, and I have this distance to be x, as I called it x. You can call it whatever you like, and the whole distance, as far as I know, that is 3 meters. So I can use similar triangles. The idea is, this is alpha, the slope here in the W is same as the slope in the 1.5. So I'm going to take tangent alpha to be equal to W opposite over adjacent, W over X will be equal 1.5 over 3 meters. And then I found a relationship between X and W. W will be equal to approximately 0.5X. This is W, okay? After that, what shall we do? Basically is I have to take the summation in the shear forces at this point, at W, to be 0. Why? Because the shear force here is 0, the internal force is 0. So if I took it to be 0, I would be able to what? To find X. Okay, so let's get started. I'm going to delete the angle and stuff. Yes, I'm going to delete everything, by the way. Yes. This is a small cut. I took a cut under W, under maximum shear. No, this is X, and this is W, will be equal to 0.5X. And this is the loads, as you can see. And this is the support A. I have here 0.75 kilonewton, as determined previously. So this point, I know that this point, the shear will be equal to 0. When we take a cut, we have a normal force, a shear force, and a bending moment, right? I know that the shear force here is 0, because the maximum moment will be 0, as you can see from the diagram. Look, this point, shear will be equal to 0. So I can take summation in the force direction to be 0 and find X. So first of all, I'm going to convert the W equals 0.5X into point load, okay? 0.5X times X by 2, right? I'm going to get 0.25X squared. This is the load. If I took summation in the forces in the Y direction to be 0, I will have this shear force will be 0, so I will not include it. I have 0.75. I have minus 0.25X squared to be 0. And X will be equal to square root 0.75 over 0.25. X to be equal 1.73 meters. We found X. I'm going to write X here. This is our X, which has become now 1.73 meters, and the moment max basically is the integral of the shear. Is the integral of the shear diagram. If we integrate this area, this shear area, we are going to find the moment diagram. So the integral of this area, this shape is parabolic shape, and its area is known for me. I know it. I'm gonna call it moment 1, for example, and I'm gonna write it here, moment 1 to be equal. The area is you have to memorize it. It's 2 over 3, and it will be given in the exam. I think you don't have to memorize it. 2 by 3 times the height 0.75 times the length 1.73, and moment 1 will be equal, we use the calculator, approximately 0.865, the moment max to be 0.865 Newton meter. This is our maximum moment, and how the moment will behave I'm going to show you right now. I'm gonna extend a little bit like this. I'm not going to extend too much because I have another method for you, the function method. So yeah, the moment will be maximum at this point. At this point, the moment will be maximum. So you have to draw the moment. Always the moment diagram will be opposite to the deflection shape. So it will be like this. This is the moment max, which is 0.865 kilonewton meter, and it will go here, this small area, this distance to be what? 1.27 if we subtract by 3, and it will go down normally like this. Okay, this is the moment max, and in order to find the moment max using the function, it's very easy. You have to take a moment function. You have to take a moment function. We have here moment. I'm gonna call it moment not, and take a moment function. In order to take a moment function, you take summation in the moment, in the counterclockwise direction to be positive. I have moment 1 or moment not, the same moment, and I have plus 0.25x squared divided by 3. 0.25 divided by 3, approximately 0.083, 0.083 x cube, because x by 3 you multiply by the lever arm, this distance to be x by 3, okay? And I have 0.75 kilonewton, which will cause negative or clockwise moment, 0.75 times lever arm, which is x, to be 0. And moment net will be equal minus 0.083 x cube plus 0.75 x. And this is the moment function. And based on this moment function, after you find x, you substitute the x value in this moment function, and you will get the same answer, 1.73 cube plus 0.75 times 1.73, and you will get the same value. You can take the calculator, minus 0.083 times 1.73 cube plus 0.75 times 1.73. As you can see, I got 0.867 kilonewton per meter, and approximately is the same value that we found before. And we can check our answers, our solution 7-51. Hopefully you found it, by the way. Yes, as you can see, the x is 1.732 meters and the moment max is 0.866 kilonewton per meter, as we found. And thanks for watching. If you have any problem, never hesitate to ask me. I will solve all the problems that you want, from the zero book from chapter 1 till chapter 25. Thanks for watching and see you.